everybody. Today is the Friday, 21st August 2020. I'm going to give lectures in electronics packaging. That's going to be the first chapter of my book. Mainly we're going to talk about reliability of electronics packaging system. I will start with the Arrhenius equation. That's the for failure rate calculation. When we're talking about failure rate, that's represented by lambda, and the failure rate can depend both on temperature and also time. Of course, when the time passes by, you will have more failure rate because it's worn out. And also for the temperature, it does mainly affect the failure rate. You know that, right? In the real life or electronic system, when the temperature gets higher, more likely the failure rate going to increase. So that what we're going to talk about are both factors that affect failure rate. So let's get started with the failure rate. That depends on the temperature. In this case, going to be the junction temperature represented by T and subscript J. Okay, J stands for junction. Arrhenius equation is used to calculate the failure rate. According to this equation, you can see that the failure rate equal to A plus B exponential negative C multiplied by 1 over Tj plus 273 minus 1 over 298. And you know that 273 is nothing more than used to convert the temperature in degrees Celsius to Kelvin, right? Or absolute temperature. And for the last term here, 298 actually is comes from 273 plus 25 degrees Celsius, and that's also in the unit of Kelvin. And 25 Celsius, that actually is the ambient temperature or room temperature. It's just like reference temperature. And A, B, C are constants. Now, if you analyze the Arrhenius equation, you can see that when Tj equal to 25 degrees Celsius, both terms going to be equal, right? So this makes about 0, and you have exponential to the power of 0. That's give you 1. So you end up with A plus B. For example, if A and B are equal 1, that means your failure rate going to be 2. And now let's consider for the very, very high temperature, for easier to analyze. When TJ is very high, this term drop compared to 1 over 298, right? Because the denominator is very large, so this term is very small compared to this term. So you're talking about like 1000 degrees Celsius, or 2000, whatever. So you end up with exponential of the positive number, right? Because minus and minus makes plus. So the whole term decreases or drop. This one is very small. So you end up with the failure rate. The failure rate is going to increases. Correct? Because this gives you exponential to the power of positive number. So this term is getting larger. So you get lambda of failure rate is greater than 2. So that corresponds to higher temperature. You have the failure rate, higher failure rate. Now, if you have a very, very low temperature, just give you easy to analyze. Let's make Tj equal to 0 degrees Celsius. So this term become what? So this one is 1 over 273. Is smaller than this number. So this one give you positive number. So you end up with exponential to negative number, or b divided by a positive number. Let's give you a smaller failure rate, or the failure rate decreases when you have a lower temperature. That's what you expect. Okay, so that's just give you ideas how to analyze the Arrhenius equation. Now, take a look at the example. The problem 1.110 at the end of chapter 1. As you were to prepare a graph of lambda, or the failure rate as a function of junction temperature of Tj ranging from 20 to 150 degree. Let A equal to B equal to C equal to 1 for this initial determination. Discuss the effect of the higher temperatures on the failure rate. So let's work it out. From Arrhenius equation, you have lambda going to be equal to 1 plus exponential of 1 over Tj plus 273 minus 1 over 298. And that's what you expect, to plot. You can use Excel. For the x-axis, that's going to be your junction temperature in the unit of degrees Celsius. And for the y-axis, it's going to be the failure rate. So Tj start from 20 to 150 degrees Celsius. Okay, you can do it. I don't have to show on Excel. Now the other term related to failure rate is the mean time between failure, or MTBF for the short. That's going to be 1 over lambda, or 1 over failure rate. So what opposite of the failure rate? is the reliability, correct? Because if the failure rate is very large, you have lower reliability, or your system is not good. You expect lambda to be very small, so your reliability is going to be a larger number. That's what you expect. You might have seen MTBF and MTTF. Well, MTTF, T stand for 2, but B stand for between. They both are mean time of failure. But MTBF is going to be a repairable product, but MTTF, that's for a non-repairable product. To get better idea, let's take a look at some examples. If I want to test 1000 devices for 20 hours, let's say 20 hours, right? And for after 20 hours, 4 devices fail. So what MTBF, or mean time between failure, is going to be? You can apply this equation. The definition of MTBF going to be equal to units tested, start, how many units of your product you want to test, multiplied by how long of hours, the unit of hours you're going to test, and divided by the number of units fail. That will give you your MTBF. Same. If you want to analyze the equation, you can see that if no units fail after you test your products for a certain time, MTBF is going to be very large, right? Because you divide it by 0, this gives you infinity. The more number of units fail, the lower MTBF is going to be. That's how you analyze the equation. So that makes sense. So let's get back to our example. You want to test 1000 devices for 20 hours. So you have 1000 multiplied by 20 hours. And you have 4 devices fail. You divide it by 4, followed by this one. This gives you 5000 hours per failure. That's the unit of MTBF. You also be able to find the failure rate because it's the 1 over MTBF, or 1 over 5000. So your failure rate is going to be 2 multiplied by 10 to negative 4th failure per hour. That's the unit of your failure rate. Okay, so you already know how to calculate for MTBF. Now you move on. You want to know the probability, or the probability that the device still working or still operates when you operate your device for a certain time. How you calculate for that? Well, we have equation. The probability that device still working when the time passed by, that's going to be PT. P represent for probability, and the lowercase of t represents time. That's going to be equal to exponential negative t over MTBF. Okay, let's analyze the equation again. If your t very large, that means you still running your system or your device, whatever. So your probability is going to be close to 0, right? Because you have the power of negative number. So it's become 1 over exponential of a positive number. And then if you not operate your system or your device at all, so that's mean your t going to be 0. Your probability that device still working, is still become 1. That's mean 100%. It's still okay. It's still survive. It's still working. It's still be able to operate. So that's very easy, for the equation for probability of survival of your device. Let's take a look. From the previous calculation, you have MTBF become what? I think I put this wrong. Sorry about that. This is supposed to be MTBF, supposed to be 5,000 hours. Okay. So let's take a look at when your operating time equal to MTBF. Then from the equation, this gives you a probability of survival to be exponential negative 1, right? Because your t equal to MTBF, your operating time, and that gives you a 0.37 or 37%. So this means that there is the 30% probability that the product will operate for t equal to MTBF or equal to 5,000 hours without a failure. Now you're probably familiar with the bathtub curve, so just take a quick look. What does this mean? Well, you have 3 regions of time or operating time. You have t from 0 to t1, t from t1 to t2, and t is greater than or equal to than t2. The first region they call infant mortality. You have a decreasing failure rate. FR stands for failure rate. And then from T1, T2, 2, we call normal life, or you have constant failure rate. And the last one is spread out region. You have increasing failure rate. What does this mean? Why it's become like this? Well, when you finish your final product, or the final process, you're ready to ship your products to market, right? You have to test first, because your system is not only have 1 or 2 components or parts, but maybe they have like 100, 200 parts to components. You have to test, you have to analyze. So when you just have your final product out of your process, there's still some failure parts in your system. When you fire it, you replace with a good one, good components. So your system failure rate decreasing, right? Because you replaced the bad one or the failed components with the good components. As we can say, like no perfect, just like yield is not 100%. So you have to do your best by replacing the failed components by the working component. So your failure rate is decreasing. And then after that become a constant failure rate, because your system is just close to a perfect operation. You have almost perfect components working, so you can use that for a while. Just like cars, you bought car from a dealer, you have like warranty for 3 years, for 4 years, 5 years, because they is pretty sure that they already test the car before they transfer the car to you. You have constant failure rate in the normal life region. And after that, for the time being, of course, some parts will worn out, because they're like you cannot use that system for ever. Okay, so that's the review of bathtub curve. Now take a look more examples. Problem 1.13. If you drop a box on the floor from, say, a height of 3 feet, determine the oscillating varying impact. What assumptions did you have to make in your analysis? You need to consider 2 separate situations. One, before the impact, this is your ground. And I apply this equation, like you learn physics from the first year or high school. V squared equal to U squared plus 2AS, where V is the final velocity before the box hit the ground or before the impact. U is the initial velocity. Of course, it becomes 0. You start dropping your box 3 feet above the ground, so your initial velocity is 0. A is the gravity. So you end up with your V squared equal to 2gs and V equal to square root of 2gs. Next, during the impact, use the same equation, but this time your V, the final velocity, becomes 0, because it stopped on the ground, right? It cannot go anywhere. And your U squared is the final velocity of before the impact, before it hit the ground. So you represent U by 2gs. You rearrange the equation, you have your A. That's what you're looking for. The relation that's become negative G. It's still like gravity. The magnitude is still the same as the gravity, but the opposite sign. That's tell you this is the deceleration, not acceleration. Okay? Okay, the last page. Problem 2.21. If your PC memory card contains 640 kilobytes, how many memory chips are installed on the board? If the chips are, 64 kbit, 256 kbits, 1 megabit, 4 megabit. So you're talking about memory card, and you also memory chip. How many memory chips you need to make memory card for your personal computer? You're looking for the total of 640 kilobytes. Well, just look back the definition of bit and byte. 1 byte equal to 8 bits. Bits for digital logic can be either 0 or 1. Okay, so for 1 byte you have 8 bits. 1 byte. You can be the digital logic can be either 0 or 1. Can be 0 or 1. So you have 8 bits to make 1 byte. And I also tell you the total combination of 1 byte. Since the 1 bit can be either 0 or 1 as digital logic, so you have total combination, to the power of 8. This gives you 256 combinations, or you can make 256 codes. So think about, you have a flash drive, you bought it, it's come with 120 gigabytes. You have very small chip inside your flash drive. Incredible, It can have memory 120 gigabyte. So for a 64 kbit chip, you want to find number of chips to make the memory card of 640 kbytes. You simply divided 640 kbytes by 64 kbits chip. Okay, K is the 10 to the power of third, or 10 to the cube. You multiply by 8 to make bits, because 1 byte equal to 8 bit. You divide by 64. K is the 10 to the cube. So that's give you 80. That means you need 60 memory chips. If chips have a memory of 64 kbit. Okay, it's nothing much. It's just only about math. But the main point you need to understand, the relations between bit and byte. Of course, you probably know about it, but maybe you forget. You not only do math, but you need to understand this one too. That's how you will become an engineer. So the conclusion, very simple. The higher bits of memory chip, the smaller the card is. Right? Okay, so that's all about lecture number 1 of the chapter 1. So that's it. I think for chapter 1 I have only 1 lecture. We will talk about chapter 3 next time. That will be more complicated. Going to be about our transmission line, about our microstrip line, and circuit analysis. You learned that before, but you probably gone with the bin long time ago because you are senior. Okay, I'll see you in next YouTube. Okay, bye.